Alright, hello together and welcome to our first video in functional analysis. We will get straight to it, starting with normed linear spaces. So as you see here, we will begin with section 1.2. This is because in the lecture notes, I follow the enumeration of the lecture notes. Section 1.1 is a review of material that is covered in metric space modules and linear algebra modules. So we won't go through those again, but I refer to results, that's why it is in the lecture notes. Now, normed linear spaces. So this is the first important type of vector spaces that we will be operating with in our module. So what is a norm? A norm on a given vector space X. Here we will only be interested in vector spaces over either the real or complex number field. In general, it does not matter whether you work over R or C. If it does, then I will explicitly write this in the results that we're going to discuss. Here, a norm on such a vector space is just a function, gets the standard notation, so the 4 vertical bars, and you put the input vector inside. So it maps that vector to a non-negative real number such that 3 distinguished properties are satisfied. Number 1, this is the positive definiteness, says that the only vector whose norm is equal to 0 is, well, the 0 vector. And that makes sense because the norm, geometrically, it will be a way of measuring the length of a vector, and, well, the only vector that gets length 0 should be the 0 vector. So that's precisely what criteria number 1 says. Number 2, similarly, this is the homogeneity. That is to say, if you have a multiple of a vector lambda x, homogeneity, then you can compute its length by just taking the length of x and then scaling it with the factor lambda. That is also clear, geometrically at least, intuitive, I want to say. And then the third one, this is the triangle inequality. Just if you have 2 points, say, in the plane, and you want to go from one to the other, the fastest route you want to do this is along the diagonal, right? This is what the triangle inequality really says, but here it's in much general spaces, okay? All these 3 properties, once you have a function that maps to non-negative real numbers with those 3 properties, then you call it a norm. Should you have, in an example, a vector space with a distinguished norm on it, then we will say this forms a so-called normed linear space, okay, or abbreviation NLS, okay? As you will find out as the weeks pass, all the vector spaces that we will be discussing in functional analysis are actually special cases of normed linear spaces. Okay, good. Now, very important to notice is that any normed linear space, so here's our standard notation for it, this will always be vector space X and then, well, the distinguished norm on it. There might be infinitely many norms on one given vector space, so if we talk about a distinguished norm, we should indicate that, and that's what I try to achieve here with this notation. Now, if you have such a normed linear space, then this is always a metric space. Okay, this is probably known from, well, if you combine metric space modules and linear algebra modules together. So here's your standard sort of canonical metric, right? So that in particular means that all the results that you have learned in metric space modules, they carry over here to the normed linear spaces to functional analysis. So all the topological results about open set, closed set, continuity, compactness, connectedness, everything carries over to the normed linear spaces. Okay, good. So these are the first types of spaces that we'll be playing with, the normed linear spaces. And now, of course, what do I mean by playing with? Well, we will study functions on them, right? Specific functions that respect, on one hand, the vector space structure, that will be the linear functions, and then on the other hand, functions that go well with the norm, and those will be the bounded functions. Okay, here's the definition: a bounded linear transformation from one NLS. So now here, since I will be having 2 normed linear spaces, I will indicate that in my notation. So the norm on the first one, on the X space, gets a subscript X, and likewise the norm on the second one gets a subscript Y, right? So after all, those 2 don't have to be the same, okay? All right, so a bounded linear transformation, that is a function t from one to the other with two properties. Number one, it respects the vector space structure, and this is simply saying it is a linear function. All right, so it takes linear combinations in the x space to linear combinations in the y space. That is a property that you have for sure encountered in linear algebra class as well. Okay, so this is here that word linear in the transformation. Now, what about boundedness? That's typically something that you don't encounter in linear algebra, but that plays an important role here in functional analysis. So that's the second criterion. There exists C positive, so that for all vectors x, the norm of the image, Tx, cannot exceed multiple C of the norm of the pre-image x in x space. Okay, so this is the only criterion that point to where you actually see the norms in action. In the linearity requirement, you don't see them, right? But here you do. Okay, and if you can find one constant C, so that this is true for all points in the vector space X, if the map is also linear, then you call it a bounded linear transformation. For me, I use the convention that if I map from one space X to a different space Y, then I call it a transformation. If I map from space X to itself, I call it an operator. Okay. The bounded linear transformations or bounded linear operators, they play a very important role in this class. So we have some shorthand symbols. Lxy, this is the set of all bounded linear transformations. And likewise, if you map from one space into itself, if you're in the operator world, I just write Lx and call them then bounded linear operators. Right? Okay, good. So these are our first two concepts, the normed linear spaces. They're also probably, you have encountered them maybe in linear algebra. And then the bounded linear transformations. They are certainly the part about linearity has occurred in linear algebra, but now we add to that boundedness. Okay, good. Now, here is one theorem to rule all of them, namely a classification theorem. So it turns out we can classify exactly all bounded linear transformations or normed linear spaces. Okay, so let's do it. Let's start with a linear function from one normed linear space X to another one Y. Again, notice here I indicate this dependency X and Y in my norms. Then as it turns out, those 5 statements here are equivalent. Okay, T is continuous at one point, T is continuous at the origin, T is continuous everywhere, and that is equivalent to boundedness on the closed ball, and then boundedness in number 5 everywhere. Okay. At first, maybe if you see this for the first time, it's quite remarkable, but actually this really is the linearity at action throughout. Okay, so we'll prove it. First off, some of those implications, they are trivial, because for instance, if you start with continuity at all points, then certainly you have it at the origin, and if you have it at the origin, then you have it at least one point, namely the origin, right? So 3 implies 2 implies 1, needs no further comment. Likewise, if T is bounded everywhere meaning in the sense of this definition, so there exists one constant, so that for all x everywhere you have this bound up there. Well, if this is true everywhere, then of course it's also true in particular on the closed ball. So 5 goes to 4 is clear. And now I also claim once you have the boundedness on the closed ball, then you have immediately continuity at the origin. Okay, that's maybe not clear right away, but it is really easy. So let's do that. So y 4 implies 2. Well, so here's a simple computation. If x naught is equal to 0, then if T is a linear map, then it maps the origin to the origin. That is a property that you know of from linear algebra. So what I have here is T of x minus T of x naught. So I want to show that boundedness on the ball implies continuity at the origin. That's why you want to estimate this difference here, T of x minus T of x naught, right? So, but what is this? Well, this is t of x, because, well, 0 is mapped to 0. Okay, and now let's use a little bit of trickery here. So t of x I can write as this. Well, at least if x is different from 0. And why is this? Well, because my function is linear. So this scalar here I can pull inside the argument, and then it will cancel out the denominator, which is the length of x, well, because I'm not sitting on the 0 vector, right? So this is true. Now also here allow me to indicate that these here are norms on y, whereas the ones with x are norms on x. Okay, yeah, but now what you can do now is now you use that the norm is homogeneous. So this factor here you can pull outside, right? So what you have is t of x in y space is x, and now it would be the length of x. Yeah, but if x naught is equal to 0, I can just subtract here a 0 without changing the result. Right, so you have this. Now why do I want this? Looks silly. Well, look at here. So this is equal to that up to that prefactor here. Yeah, but this prefactor, what happens here? Inside there is a vector which in norm is what? Less than or equal to 1. It's actually precisely 1, but okay. So, but it's less than or equal to 1. That means this is a vector in the closed unit ball. And remember, I'm going right now from 4 to 2, so I have boundedness on the closed unit ball, right? So this means this here is less than or equal to c by 4, by assumption, right? So you get the whole thing less than or equal to c x minus x naught in x space, okay? And now why is this the continuity? Well, if you read this and equal to this is actually Lipschitz continuity, right? With Lipschitz constant equal to that constant. So in particular, you get continuity if you have Lipschitz continuity. Okay, so that's why 4 implies 2. All right, so now for the rest. Well, there's many ways to establish those equivalences, so I will go just one route, and then you can check once that route is rigorously established, then you have that all statements are equivalent. Okay, so for the rest, we will use following facts, general facts about continuous maps actually on metric spaces. So there are some equivalences itself that were covered in metric space module. So T continuous on X. Okay, that you define usually with a definition of delta epsilon, but then you show that this is equivalent to the following thing. If xn is a sequence in X space that converges to X, then the image sequence also converges. Okay, T of X Sn goes to infinity. Okay, and if this works out for all convergent sequences in X, then T has to be continuous. Okay, so this is equivalent. That will be used, and then the other one, the more exotic one, but actually from a topological viewpoint, the best one is that pre-images of open sets are open. So here my notation, this is the pre-image, so those are all vectors in X, such that T of X is equal to B, is open for any open B in Y space. Okay, so these three equivalences, this one and that one, they are proven in a modular metric spaces, so they carry over here to our non-linear spaces, and for those I will use those in our upcoming proof of the remaining equivalences. So let's put this maybe in green. Okay, good. Now let's start with something. Let's do 4 to 5. This is more or less what I already did up there. So we will show that boundedness on the closed ball gives you boundedness everywhere. Well, for any non-zero x, we have that T of X. So this is the same trick I used earlier with the linearity, sort of multiplying and dividing by the same quantity. So you have this, then this guy here in norm is, well, precisely equal to 1, so it's particularly less than or equal to 1. Hence, if you estimate the whole thing, you have t of x in y is, well, this is still an equality. I haven't estimated yet. Tx in x, y, but now I do, because this is a vector in the ball. I already used this notation earlier, b10, so these are all, maybe let's use the closed ball, that's better, x less than or equal to 1, and since by assumption t is bounded, I get immediately this. Okay, so boundedness everywhere. Good. So that equivalence is established. Force equivalent to 5. Yeah, I only did it here for non-zero x, but of course, if x is equal to 0, then since the value of a linear map at 0 is equal to 0, it's also bounded at 0. Okay, so this works out. Now, next, let's do the following equivalence. Let's do 1 to 3. And for that, we will use one of the criteria that I had earlier that were equivalent to function being continuous. So suppose t is continuous at some x naught. And now I will show I have continuity actually everywhere. So, and x in x arbitrary, I will show that t is then also continuous at this arbitrary point x. Okay, and we will use sequence criterion. So if xn converges to x, then, well, let's look at this funny difference here. So what can I say about this sequence? So xn minus x plus x naught. So that's the nth term in a new sequence. Well, if this here goes to 0, then by the limit laws, this here goes to x naught as n tends to infinity. So by linearity of t and limit properties, I will tell you which ones I mean. So first the linearity, txn minus x plus x naught. Well, this is txn minus t of x plus tx naught. Okay, that's the linearity. Now, since you have continuity at x naught, remember that is equivalent that any sequence in x space that converges to x naught is sent to a convergent sequence in y space. And of course, now the sequence that I'm going to take is this one. Okay, so this one goes to x naught. That's why in y space it goes to the appropriate limit, which is t of x naught. Okay, and now you have this here is the large n limit of this one. So now you use the limit properties and in a sense cancel this out. So what remains, txn minus tx then goes to infinity, has to go to 0, right? And that's precisely what you want, because that is then giving you the continuity at the arbitrary point x. So continuity at x. Okay, so we have this, and then I will only have to do one more, and then you have to check that indeed this is sufficient to conclude that all of those 5 things are equivalent. Finally, show 2 to 5. So 2 to 5 is the continuity at the origin implying boundedness everywhere. Okay, and for this we will now use that pre-images of open sets are open. Okay, so from continuity at the origin, okay, we get that the pre-image of any open set around the origin has to be open in the X space, right? So let's take one open set, which is the open unit ball, right? So here again the notation, these are all X and X, whose length is strictly less than 1. We get that this has to be open. It's open in X. Okay, so what does this mean for a set to be open? Well, that means you can fit open balls inside. Okay. So what do I get? There exists, and I'll explain why, b delta 0 in X inside t minus 1 b1 0, meaning if X in X space is less than delta, then t of X in Y space is less than 1. And why is this? Well, you just need to remember how this is defined. So what's the preimage of this? These are all X in X, such that t of X is inside the ball of radius 1. Yeah, but that means that the norm of t of X is less than 1, right? So t of X is less than 1. And this has to be an open set, so there is some b delta 0 sitting inside, and that's precisely what's written here. So if X is less than delta, meaning X is in that b delta 0, then it has to be in this set. Well, that's precisely what's written here. Okay, so we have this. Good. Okay, so now what do we do with that? Well, but if X in X is arbitrary and epsilon positive, then, well, let's look at this point here, delta X epsilon plus X. This is a point in X space, and what is the length of it? Well, you use the homogeneity of the length, you can pull out the delta, and then what you have is you have the norm of X divided by epsilon plus the norm of X. But if epsilon is positive, well, then this is strictly less than 1, so then the only thing that remains is the delta. So this is less than delta. So meaning this point here, this is sitting inside your disk of radius delta centered at the origin. Okay? So then, and therefore, by linearity of t, okay, now we evaluate t delta x epsilon like this in Y space. So remember this point here, delta x over epsilon plus norm of x is inside my ball of radius delta, center at the origin. So this means the image here is bounded above by 1. Okay, and now you use the linearity, you can pull out a lot of things, namely delta epsilon xx, and then what remains inside is just tx of y. Okay, and now you shuffle this around, you bring that whole fraction to the left, it's positive, so nothing happens here with the equality sign. So t of x y is less than 1 over delta epsilon xx. Since this holds for any positive epsilon, you can let go epsilon to 0. The only need for this epsilon surgery is because you wanted a point that satisfies here the strict inequalities. That was the only need for it. Okay, so now you let go epsilon to 0, so you get t of x y is less than or equal to constant Cx, and the constant is precisely this 1 over delta, which is positive. Okay, and this works for all x, so you have shown that t is bounded everywhere, and that's precisely what you wanted in going from 2 to 5. Okay, that's it. As I said, now you have to convince yourself that this is enough to conclude that all the 5 statements are equivalent, but it is.